Okay, welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk, but if you have questions, you can unmute and ask questions. Or use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now, let me briefly introduce our speaker today. It is an honor to host Professor Yan-Nei Chen in Mathematics Department at University of Massachusetts, Dartmouth. Yan-Nei received his PhD in mathematics from School of Mathematics, University of Minnesota in 2007. He then worked as a postdoctoral researcher at Brown University before joining the Department of Mathematics at University of Massachusetts, Dartmouth in August 2010, where he currently serves as a full professor. Dr. Chen's research has been supported by the NSF, AFOS-SR, and ONR via University of Massachusetts Dartmouth MUST program. His research interests are in numerical analysis and scientific computing, in particular finite element methods, reduced basis methods, and other fast algorithms, uncertainty quantification, design and analysis for machine learning algorithms. He has graduated 5 doctoral students and initiated the University of Massachusetts Dartmouth's accomplished program via an NSF grant to provide students in need financial, social, and curricular support. Today, Yan-Nei will talk about GPT-PINN and TGPT-PINN, Generative Pre-Trained Physics-Informed Neural Network toward non-intrusive meta-learning of parametric PDEs. Please enjoy and expect a wonderful talk. Now, let me ask a couple of questions to Yan-Nei, just to get to know you better and make this seminar somewhat informal. So first question, here we go. Obviously, you are passionate about scientific machine learning. When and how did you get into this field and started to do research on them?
Thank you, first of all, for that's a long bio and a long title. Thank you for reciting them. Appreciate it. So I've been working on reduced basis method, which is by itself a machine learning-ish algorithm. So I sort of know the machine learning field a bit, even without doing, explicitly maybe the more modern scientific machine learning projects. So it has been in my mind to work on. I saw some connections to work on, the neural network specific stuff for a few years, and I started working on it together with a student, Sean Kui, about 2 years ago to less than 3 years ago. So I'm a newcomer here. I'm looking forward to learning from all the experts.
Okay, great. And second question is, you're passionate about the teaching and mentoring students, right? So if you can, share some, thought about, why you enjoy, mentoring students and, teaching them and etc. That would be awesome as a professor.
I think part of it is maybe self-centered, to be honest. When I get excited about the stuff that I teach, so when I'm able to enunciate what I thought this concept is about, I got excited myself. I think anecdotes point to that side of that kind of excitement is somewhat contagious to students. Students get excited too, and of course there's in the more traditional stuff. We put in the work and you see progress from students. Most of the time it's probably a bit hard and challenging, just like research, you have setbacks. But once in a while you see a great progress, and that make it all the whole effort worthwhile. So I think that's, seeing that growth, seeing on the undergraduate level and the graduate level, that's what this profession is about, and I truly enjoyed doing it.
Sounds wonderful. All right, the stage is yours.
All right. Thank you so much, Yang Song, for inviting me to this seminar. Thank you for your work in doing this DDPS seminar and giving me the opportunity to talk to your audience. I certainly treasure this opportunity. Today I was reflecting on the luck that I had last June, meeting one of your group member, Tony Chang. I'm not sure. I don't see the audience. I'm not sure if he's here, but I appreciate talking to him last year at Morgan State.
He's here.
So as Yang Song, all right, as Yang Song just announced, so I'm going to talk to you about GPT-PINN and the TGPT-PINN today. And I have to, admit that the title is somewhat of a gimmick, but I think it's literally true. Hopefully you will be convinced. So this is joint work. I will spend most of the time talking about the GPT-PINN, which is a linear reduction method in the PINNs fashion. So let's say the linear part. I spend a few slides towards the end to talk about the extension to the nonlinear part. And the first part is joint work with Sean Kui, a fantastic undergrad student who is going into a graduate program soon. And the second part was just submitted a few weeks ago with Ya Jie and Akio Narayan and Zhenli Xu. All right, so here is what I was hoping to be a take-home message of the seminar today, and the GPT pin to pin is what RBM is to FEM. So we have the finite element method, we're solving equations, and in the multi-query setting that the wrong people we all care about, there's a one particular method is called reduced basis method, and in the today's world we use neural network for things. With kind of waving fashion, let's say the pin is basically also a PDE solvable, and GPT-PINN is basically a extension of RBM to the pins to the scientific machine learning field. So this a little bit of diagram is the overall message. His outline, I will give you a brief intro of the so-called PMO, the projection-based model order reduction. And then I spend a slide on pins, and then talk about how we go from PINN to GPT-PINN. And then show you some result for the GPT-PINN, and finally again from the linear to nonlinear extension. So the multi-query setting, I'm pretty sure this community is quite familiar with. So here we have simulations, aerodynamic simulation, or maybe the radar signature type of simulation. We need to change things, maybe the shape of the car, right, or the flow field, or angle, material of the fighter jet, all those things, and you want to optimize the aerodynamic performance of the vehicle or the radar signature to minimize that of your object by tweaking your input, the shape, and all those that were just mentioned. Or perhaps you want to perform sensitivity analysis, UQ. So all these situations, you need to solve a parametric system over and over. So you need to the forward solve has to be performed many times. And we cannot really afford to always use the full order model for those forward solve. So this is a quick slide on the PMO with some references, and here what I'm showing you is a electromagnetic problem, and what you would discretize the domain, and you see a lot of triangles on the surface, and that's basically there's a large number of degrees of freedom to show those degrees of freedom. And the projection-based model order reduction strives to accelerate this simulation. So in particular, for the RBM, the linear reduction, here is the particular answers. So what it does is that it explores the parameter domain and find a few representative parameter values. And then you use your favorite forward order model, a full order model, to solve for the solution at those locations. So those are the solutions that I use that I'm giving here, the U1, U2, U3. And for the other parameter values, you try to come up with a surrogate. So here is a linear combination of your pre-selected, pre-computed solutions. And the task then is, of course, how do you find those n dimensions and pre-computed solutions? And on top of that, given those, how do you calculate the coefficients, C1, C2, C3? I'm going to shed some light on those. So this you give me mu, I calculate these C's, C1, C2 to Cn. I'm calling that a parameter to code map. So for the PMO, there are certainly other methods how you calculate this. C maybe by interpolation or a learning, but the traditional PMO is based on solving the PDE in the reduced setting. So here's what I'm trying to emphasize: it embeds physics. So we have equation, a simple reaction diffusion equation. I'm taking mu as the two parameters. And the weak solution for the PDE is, we look for solution in the H10 space. We solve the weak formulation. And the final element is discretizing the space H10 by a final element space VH, perhaps a piecewise polynomial, for example. And it's discretize the bilinear form A by AH, basically numerical differentiation, numerical integration. And by doing that, you're solving a discretized formulation, and in another space, in the space of VH. You go from H10 to VH. So the reduced basis, I'm using very loosely the term structure preserving. The reduced basis is one step toward along this line. So it looks for another space, which I'm calling WN. WN is a subspace of VH. Other than that, and then of course the test function is in this conforming method in the same space. Other than that, there's no change. You solve the same formulation. That's what I loosely meant by structure preserving. There's no, I'm not talking about physical structure preserved. So that's the traditional finite element, the reduced basis method. And there's a bit of theory behind all that. The key concept of the chromograph and widths. So essentially, what it does, it measures to what extent your manifold, your solution manifold, you by going through all the different mu value in your parameter domain, how that solution manifold can be approximated by an n-dimensional space xn. You take the distance and then you find the best possible case in theory. And this distance, of course, is defined in this way. And for many problems, especially problem with a bit diffusion, so these n widths decay fast, exponentially fast. So that would allow us to come up with a space Wn that would approximate the original finite element space really well, and that's you give it hope that you can find a really good surrogate. So the key question of how do you construct that space Wm, right? There's a widely used method called POD. The POD type of approaches, what it does is you sample your mu domain. I sample like let's say, a lot. And then you do your SVD. And you basically then you truncate down, the keyword is truncate down. You maybe you have 10,000 solutions, snapshots, and you truncate, you take, the first 10, right, for example. So you ended up using a lot more than you ended up querying the further model a lot more times than the one you obtained in the end. So that 10,000 is much larger than 10. That's what I'm trying to say here. So that's perhaps a top-down approach. You go, you sum a lot and then you cut down. And the RB is advocating for a something called greedy algorithm. So what it does is a bottom up. So we go from empty set to the release basis space, which I will describe more later in the GPT-PINN setting. The end result is that if you only need 10 dimension space in the end, you only, by the time you construct your space, you only have queried 10 times of your further model. So that's a big difference. So that's the message that I'm trying to emphasize here. The amount of form data, further model data, is going from big to small by going from POD to RB. And going back to the key part of the P2C map from mu to C mu, there certainly have been other approaches, so the neural network type approaches, and I'm listing just a few of them, and that is by far not a complete list. And started from around 2018-ish by Haseben's group with the POD and there was and this is a landmark paper by Karburg and co-authors. Proposing the autoencoder in this reduction setting, and the overall message here is that once you train the map from mu to C mu, you give me a new mu, I simply evaluate the map, the trained map. So map recovered via direct evaluation of Fn, a direct evaluation. And I want to point out there's a nice theoretical paper here, and what they essentially proved is that for problem where RBM works, basically there is a low rank structure that exists a DNN that can approximate this solution map to your accuracy. And furthermore, they proved the upper bound of the size of the DNN is essentially the cubic of the intrinsic dimension. There's a nice work there. So I'm trying to put these methods to catalog them. The POD, I put it here, meaning that you need more data. So the horizontal axis is amount of data, the vertical axis is the amount of physics. The reduced model is based on the PDE, so there's a physics in it. The NM regression, you need data because you train the map by the labeled data. So you train, that's a data intensive approach in general. And as an end result, there's no physics when you give me mu, I give you the C mu. RBM is sort of in the second quadrant, perhaps a more preferred one. You need less form data while having more physics encoded. And speaking of numerical solvers, since 2018-19, there's a family of methods called PINN, physics-informed neural network. So what it does is it has this complicated function, right? It's a linear operation composed with nonlinear functions, and keep doing that, and you basically use that as your solution to a PDE. And what you do then is you use the magic of auto differentiation, and you calculate a loss, a point value, a pointwise loss, the collocation setting. And the the neural network then trains those weights W and bias B, or maybe there's something in the sigma, the nonlinear activation function, train all that by minimizing this loss. This loss not only contains the PDE, the residual, but also the deviation of your solution with boundary condition and initial condition. So in a way, it satisfies PDE and also the boundary and initial conditions. You train it until your MSE is small enough, or maybe you cannot decrease it anymore, and you take that theta as your network configuration, and that network function is then your PDE solution, right? So simple but powerful and popular idea. So of course, as somebody in the ROM community, right? Once I saw this, I was like, okay, what do we do when you need to solve a parameter-dependent equation? Of course, to people in PINN, you could just add a mu here as an input, right? So that's one way to do it. But the drawback is you are introducing a larger network, and training takes more time, or that disadvantages. So if we just look at, if we don't do that approach, and we have this, every time you have mu, you train your theta, the network configurations. And the challenges of trying to work with that is we observed there's there's not really a low rank structure within your theta. We showed a graph in the paper. And that's what I just mentioned. So some related attempts, and again, this is by far not a complete list. So I'm listing a few of them. So the first one is basically to play with those theta star, and you do a regression interpolation type of things in your parameter space, and you take the traditional meta-learning approaches. I'm calling PINN plus X. So the X is whatever approach you do with your theta star. But again, that is related with, there is no good low-rank structure from what we observed. The second is a DeepNet and FNO. So this is a more POD-based thinking. So and it's data-driven. And again, once you train it, it basically just evaluate the map. And the meta-node is taking on a more transfer learning approach. And again, the surrogate is fully data-driven. A more recent one is called PRNN by Chen, Wang, Hashaven, and Zhang. And they introduced basically to not purely data-driven, but also to incorporate a bit physics in that training, of the map. Again, once you train the map, you give me new mu, you still evaluate of the trained map. So this is what I'm summarizing here. All those methods is sort of in the fourth quadrant. Is you need more data, and the end result is a map that you evaluate for a given mu. And PRNN, I'm put it in the third quadrant here, takes a bit less data. And so the question for me to ask was, what about this second quadrant? Can we, in this setting, can we do something with less data, but more physics? And that's what I'm trying to argue here. That's where GPT-PINN belongs. And now the design of the GPT-PINN. So what I'm going back to, where I started from, the reduced basis method. So that's what inspired this whole thing. And this is the answer of the reduced basis. So you are taking a linear combination of your pre-computed and a well-chosen solution. And now, the first step is, of course, if you use PINN, you just replace that solution by the PINN, right? And what this is, if you take a look, it's just a one layer zero bias a network. You take a linear combination, you plus 0. And the n is certainly the width of this layer, and Ci is you think of it as the weight. And slightly interesting one is this this pin, the perceived theta I, right? The I's pin. For the whole network, this I's pin is essentially a activation function, but it's not the regular ones, the regular or that. It's not those. You have to put it. You have to put the customized activation function, so to speak. So that's what we did. We we have this reduced network. So it's basically only two something n1 network, and you give me the xt. I have in the one hidden layer, right? One hidden layer. The hidden layer has n networks. Each neuron is full network, and then I put the weight here, and I combine them to get my reduced solution. So the generative part is that you give me a new mu, right? So in a parametric setting, you give me mu, I basically generate this network, this reduced solution for you. There's one point to point out. One thing to point out is that the mu comes in as the as a loss function. You give me new mu, the mu decides. Otherwise, the whole network is independent of mu, right? It looks potentially confusing. But where the mu comes in is through the loss of the network. So you give me new mu that defines a loss for a particular loss for the network, and then the network goes ahead and train those C's, those weights. That's this is this simple idea. And these guys are pre-trained, so pre-trained pins, pre-trained, and you put it there. Training takes time, but once you train it, you put them as a neuron, as activation. The evaluation takes is quick. So the next point is that these guys are growing one by one, just like the greedy that I was describing for reduced basis. So we started by a 2-1-1 network, and then it grows to 2-2-1, 2-3-1, and all the way to 2-n-1. I'm going to describe the greedy algorithm later. So the sort of the features, it embeds physics because the loss, all right, you train the network by minimizing, decreasing the loss. The loss has a residual and the boundary and each condition in it. And in its small form data is a ground up approach. It starts with empties and then goes 1, 2, 3. It's not top down approach. And it has meta neurons. So by what we meant, just each the activation is a full network. So it's a network approach. And it is non-intrusive, by which I meant is you don't need the knowledge of the pin. So we have an example where we tested on Alan Kahn. We use a self-adaptive pin. We don't need to know what's going on inside those neurons in the one hidden layer there. And just like other raw methods, it accelerates the underlying method. Here it accelerates the pin. The marginal acceleration is 2 to 3 orders of magnitude. Just again, like what we see for the traditional RBM type of result. And before showing you the result, I want to mention just a couple of things. One is that the success of this is largely based on the derivatives are linear, and the whole pin thing is collocation. It's collocation in nature, right? So it's more local, and those things allow us to pre-compute. So just like wrong approaches, either is offline, online setting stages, and here we pre-compute the quantities that we need for online. So that's important piece. And another one to connect with RBM, which would allow me to describe the greedy algorithm that I promise you, is this a posteriori error estimator. So that's a key element for release basis. You need that to explore your solution space to identify the next sampling point. And that's, in RB, for people who know a finite element, that's more or less straightforward, because basically the standard residual based error estimation is scaled by your stability constant. And if we think about the neural network, the pins, the loss is based on the residual. So the MSE that I talk about. So we sort of have a automatic choice there. So we take the loss of the reduced network. That's a residual based indicator, right? So that's what I'm going to use. So here is a flow chart. So we have we set it up. You have just like the typical ROM. You need to develop a Ford model. Here I have a 4 pin ready to go. All right, and in the beginning I know nothing about my solution manifold, so I just pick my first one randomly. All right, and then I solve a 4 pin at this 1 point mu1. Okay, now you have 1 pin, so you can construct a 2-1-1 network. N is 1, so it's a little network 2-1-1 with one neuron in the middle. And then you go train it. You go train this 2-1-1 network everywhere. You sort of use your current reduced model to explore your space everywhere. So every time I record my code, I include my loss. This is residual based loss. All right. And the greedy step is that, well, I take a look at all those loss of the whole parameter domain. Is that small enough? Of course, when it's 2-on-1, it's likely it's not. So it's not small enough. So I'm going to take the one, this greedy idea, the one that maximizes my my error estimator, error indicator. And that's where I'm going to sample next, right? So it's a classic greedy algorithm, has quite a bit of theory behind. So once I determined my mu2, I go ahead and call my 4 pin again at that mu2. So now I have my second pin. So my 2-1-1 network became a 2-2-1. And then I repeat this loop. I go from 2-2-1 to 3-1, 2-4-1, and so on and so forth. And until hopefully at some point, this global, the maximum loss over the parameter domain is less than a tolerance, then we stop. We take that as a GPT-PINN network. So we tested this thing on 3 examples: the Burgers and Alan Kahn and Glenn Gordon. So they have respectively 1, 2, 3 parameter values. And this is just the setup. In the interest of time, I'm going to not dive into the details here. I'm going to show you the result of one equation. So here is the Burgers equation. And the first one is where the networks decided to sample. So we started not exactly random, but just take the middle of the parameter domain. And then you generate, you let the algorithm decide what to do next. You see it goes to number 2, number 3, and it then sort of focus more toward the lower viscosity end, and picked one here. So in the end, we showed this is the largest loss graph as you proceed this process from 1 to 9 neurons. So in the very end, we only have 9 neurons in the hidden layer. And the black curve here is our method. So we get below 2 digits, which is sort of in the PINN setting is about okay. And just to show how powerful this idea of this RB ROM idea is, when basically you move to the PINN setting, if we do a uniform sampling, so-called uniform neurons here, we just uniformly sample the parameter domain and just call and train them and put them at the hidden layer, and it's not bad. You know, it's worse than the adaptive one, but not that bad. This is more statistics of the losses, and I'm just showing you the first three modes that was calculated by the GPT-PINN. So to test that, we tested on a number of unseen parameter values, but still within the range of that it was trained. So it, you know, it does performs reasonably well with again the terminal errors with at the end of the training. And to show the computational saving, what I'm showing here is as the x-axis is a test case number. So we repeatedly call. So here the red curve is if you repeatedly call your PINN for up to 25 times, and you record the cumulative running time. All right. So for the GPT-PINN, you have this initial investment where you train it, you form your GPT-PINN. Afterwards, the slope is basically flat. The slope measures the marginal time, right? So the slope ratio is more than 100. So two orders of magnitude speed up. But of course, just like other ROM approaches, this is for multi-query. So if you need to basically need more queries than this intersection point, right? You need more than that number of for this implementation. You need more than that number of queries is worthwhile to invest in the learning stage. So for the other two equations, we got very similar result. I'm just showing you some nice pictures of the other two equations. And the speed up factor is more than the Burgers. And just to repeat myself, so the Alan-Kahn equation, we used a self-adaptive PINN developed by these colleagues, and we don't need to get into the PINN. Just take it and run it at where the GPT-PINN algorithm asks us to train, and that's it. So I want to spend perhaps the remaining time to talk about the extension to the nonlinear reduction setting, what we were calling the TGPT-PINN. So we bring back the n widths. So this for diffusion type of problem, that was a result that basically shows there's a low rank structure. So this n width decreases exponentially fast, which allows us to construct a small space to approximate the solution manifold, right? But for transport-dominated phenomenon, so here what I meant is you sample a long time, just above the same thing. If you sample a long time, there's a low rank structure. Here for the transport, if you sample a long time, it's just like identity matrix. It's the same thing moving forward. You don't really get a low rank structure if you do SVD to the matrix. And in fact, it can be proven that this, instead of upper bound like the diffusion setting, for transport dominated situation, there's a lower bound. So your width would be will not decay faster than that, this fairly slow decay. So that's the main hurdle for the linear reduction, and the reason for colleagues to start working on nonlinear reduction in the last few years. So we just very briefly, what we did is we incorporated this is not a new idea, incorporated with this transform idea. I'm listing again a partial list of result in the last few years. So what we did is basically we're adding a layer of these transforms, the transform blocks, to the GPT-PINN. And for you see each transform, for each mu I have a transform, and that's it. I'm going to show you some result to demonstrate how it works. But the key point here is that once you have this structure defined, You give me a new mu, the weights, the C's that were in the GPT-PINN, and the transforms, they were simultaneously trained by this reduced network. And it's still in the PINN setting, in the PINN fashion, meaning the PDE is incorporated as a loss function. And this is basically a nonlinear RB by incorporating this transform before putting it into the pins. And that was recently submitted paper. So to show you how it works, here is a result from the Welper 2017 paper. This is a function, is a pretty nasty function. So this is some of the snapshots as you change the mu value. So you see, first of all, they all have discontinuity, and some of the discontinuity is on the left, some of the discontinuity is on the right, and moreover, the discontinuity moves as you change the mu. All right. So this is a typical challenging setting for that calls for nonlinear reduction. So here I'm showing you some result. The gray is the exact solution. If we do a textbook Lagrange interpolation, you get this. Is the sawtooth, right? And in model reduction setting, there's something called EIM, empirical interpolation method. What it does is it uses this same family, these same members of the same family to interpolate, to use them as bases. I'm going to pick, just like RB, I'm going to pick mu1, mu2, mu3, and so on. I generate U1, U2, U3, use those as bases, as opposed to perhaps, the polynomials. And that's a purple thing. You still cannot avoid the sawtooth. But if you apply the so-called TGPT-PINN idea, you get basically identical approximation, a perfect approximation. Because the idea is it detects and automatically line up the discontinuity. Once the discontinuity is lined up, then you can do your linear combination that will be more effective. And so we applied that to a few PDEs, and I'm showing you one result here. Is a nonlinear reaction equation. So we are able to solve the family of equations, the parametric PDE, using one neuron, one big neuron, right? It's one neuron, but it's a whole pin as one neuron. So that's a nonlinear, the TGPT-PINN result. If we were the original GPT-PINN, you would need 10, but even with 10, the result is worse than the nonlinear result with one neuron. So to conclude, we have the first PINN accelerator, which is the RBM is what we believe is the first PINN accelerator that follows the ROM idea, the RBM framework. That preserves the PINN structure, relies on less data, and it's non-intrusive. It's sort of you pull an existing PINN, you can just plug it to your network. The loss is guided by the grid construction, and it naturally features offline-online decomposition, and we're realizing actual speed up in practice, and we extend it to the nonlinear reduction setting. So the code is available on GitHub, and here's my email, and I also want to acknowledge funding support from NSF, AFOSR, and the MAS program at UMass Dynamos, and we have a pretty active Center for Scientific Computing and Data Science Research. So I acknowledge appreciate all those support, and thank you everyone for your attention to the talk today.
Thank you so much for the wonderful talk. A beautiful idea. I especially like the fact that you combine the reduced basis, the framework, and with the pins idea. Awesome. Wonderful job. Okay, let's have a Q&A sessions. If you have questions, please unmute yourself and ask questions. Maybe I can start. You know, the pins, beautiful idea, very popular.
Mm-hmm.
The problem with the pins, though, is the fact that they impose the boundary condition and initial conditions weakly, like in the loss functions, one of the loss functions.
Yeah.
But I mean, for 1D problem, that's okay. But if you go to 2D, 3D, and then complex geometry, no longer trivial task to imposing those boundary condition and initial condition. And your framework, basically relying on the original PINN's framework, right?
Right. Yeah.
So those issues with the PINNs, imposing the boundary condition, initial condition, your method has that too, because we are relying on the original PINNs. If you can comment on that.
Yeah, it basically inherits
Yeah.
the advantages, but also the disadvantages of pins, right? A lot of is up for debate. I think to implement it in 2D, 3D is people certainly did it, right? In terms of accuracy and speed comparing with the traditional methods, that's a different story. It's doable. I guess there's a method called a variational PINN, and to which I'm not familiar. We know in the traditional numerical method, sometimes you don't want to enforce your boundary conditions in a strong fashion, and that would have negative impact on the conversion speed, for example, the conversion order. So yeah, so maybe some of those we have to go through the more Galerkin and more variational approach.
Yeah.
To overcome some of those disadvantages. But yeah, the overall message is exactly right. This inherits the whole framework is a PINN flavor in the reduced level. So it inherits pretty much everything from there.
Yeah. Beautiful idea, though, Yanni.
Thank you.
Is there any question from audience? Otherwise, I can keep asking. Master?
Yes.
You unmute yourself. Do you want to ask a question?
Yeah. Just a quick question.
Okay.
So in the world of RVM, like many other frameworks, there is the challenge of with dimensionality, right?
Yeah.
Meaning, the curse of dimensionality. And then forgive me, this could be a kind of naive question, but combining RBM and PINN, I'm not saying you have tried it, I'm not even saying you have thought about it, but are there ways to benefit from this combination, right? To alleviate, right, the challenge with curse of dimensionality. And the reason I asked that question is you do know that there are problems where we have many parameters, and for example, you do know that there is, for example, topology optimization, where you have thousands of parameters.
Mm-hmm.
And yeah, it's just I'm just thinking aloud, and
that's certainly a tough problem, I think, and a lot of people have been working on it. In terms of in the vanilla RB, so the vanilla GPT-PINN, let's say, we want to make sure the parameter domain is well covered. So you are doing, you know, a Cartesian grid, let's say, on the parameter domain, and of course, then you have the exponential increase. The cardinality of your test of your training set would exponentially increase with the number of parameters. The training, offline training, because every time you're exploring the domain, so the training is linear with respect to the cardinality of your training set. There are things we can sort of do to delay the, not overcome, but delay the cost of dimensionality. Maybe you want to, you know, we have some result, I think, including Yongsong's group has some result in perhaps, you know, some smarter way of sampling, or maybe you introduce maybe a gradient-based approaches. We had some result a few years back. You know, we can reconstruct. You know, we based on a fine sampling, but then with one sweeping, we can reconstruct a sort of a more, you know, area where you want to explore, keep exploring, and those areas, you know, you explore where you don't need to explore again in your next greedy step. But all that is at most delay the cost of dimensionality.
Dimensionality. Yeah.
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 That's tough one.
Thank you, Yola.
Thank you.
Related to that, if you can go to slide 11, Yanni.
Okay. All right. So where are we now? Oh,
You
wait.
have a lot of slides.
Yeah.
Oh, awesome. Okay, here IBM needs less number of data because you know greedy approach, greedy algorithm. You know the POD, you can also apply the greedy sampling. That way you can reduce the amount of the full order model data. Then you can move the POD to the same category of the same quadrant of the IBM.
Yeah. I guess by this I meant the vanilla version. Yeah. Great point. I know for like your work on the velocity, right? For example, is it G-plasty?
G-lasty, we have both of them.
Yeah, exactly. The vanilla version, right? It's
Got it.
Thank you.
All right, is there any other questions? So what is the next step? You obviously want to, you know, make the problem more complex. Like instead of 1D, you may want to extend that to 2D and then 3D and etc.
Yeah, that's certainly a very worthy direction. So right now we're focusing on so to go toward the nonlinear direction a bit more. So right now with the nonlinear, the TGPT-PINN idea works. You know, for transport, I didn't show the result here, but for transport is in the paper. For linear transport, you know, you use one neuron, you get machine accuracy basically comparing with the full order model. For other things like nonlinear reaction diffusion, and then you know, with some convection, you know, they work out well for burgers, and we're trying to do Euler equation. So for those ones, the transform blocks are not that easy to handle. So right now, the transform is simply a affine transform. You have a affine in each block of the transform layer. That's good enough for a lot of equations, but for not the case for, you know, in viscous. I mean, for in viscous burgers is still good enough for the Riemann problem, for example, or the different Riemann problems. And for Euler, that's challenging, even for the underlying PINN. So, you know, that's what we're currently working on now.
I see.
Yeah, high dimension is certainly a challenge.
Yeah.
It's a challenge for PINN, and it's certainly a challenge for the
other data-driven approach.
data-driven approach, right?
Yeah.
That's, yeah.
May I have a question?
Yeah, sure.
Sure.
Go ahead.
Yeah. Hello, Yanai. Nice to see your
Hi,
talk.
Li-Hong.
Hi. Hi, Yunsu. I'm Li-Hong on phone from MPI Magdeburg. Yeah. So my question is that so you use the shift to transform the coordinate and time. But it's different from other work because for other work, they also use some kind of construction to return back to the unshifted coordinate system. So, but it seems to me that you shift the coordinate and then you just work simply in a shifted coordinate system, and the reconstruction step in the original coordinate system is missing from your overall network. I don't know what's the difference from your overall network from the other existing network. Yeah.
In terms of the shifting idea and the scaling, right? In terms of that, nothing is new. So we basically just incorporated that idea to the PIN and the GPT-PINN setting. So included that in as an additional layer. So yeah, so I listed some reference there. Certainly, that idea is not new.
Yes. So from other work, they have two steps: shifting and reconstruction. Yeah, but it seems to me you have shifting and then you work simply in the shifted coordinate system. So I don't know whether your pins, the GPT pins already implicitly,
Oh yeah.
included this reconstruction step.
Certainly, yes. I missed that part. Yeah. So if you go back to the first layer, the input layer, right? It's kind of like that's their second step. You go back to the original coordinate. So the whole thing is still defined from the original input layer XT before the shift.
Okay.
So the simple evaluation from the whole thing means a reconstruction. Yeah.
Okay. Thank you. Yeah.
Thank you, Li-Hong.
Yeah.
Awesome. Is there any other question from audience? Well, if not, let's thank our wonderful speaker, Yanne. Thank you so much, Yanne, for the great idea and great talk. We were able to follow it very easily. You have a great presentation skill as well.
Thank you so much, Yong-Sung, and thank you everyone for tuning in today. I appreciate your attention.
All right. Thank you so much.
Take care.
Take care. Yanne, are you still there?
Yeah.
Would you mind sharing the slide with me?
Of course. Yeah, I can.
Okay, awesome.
Yeah. Of course not. I mean, I'll send to you, Yong-Sung.
Okay. Thank you. All right. Keep in touch.
Bye-bye.
Bye.